So here we're going to talk again about if I have to define what is a rock, the best I can do is that sentence on the top. And a couple things to point out. They talk about crystals, aggregate of crystals. There are crystals if you look at the right scale, sometimes, usually, but then there's usually kind of a mess because usually rock isn't just a pure intact crystal that's grown, like a granite, like a pure intact granite. There's usually then um, it's usually gone through other types of diagenetic processes. And so you get also these, they call them amorphous particles. They're sort of hard to describe. They're just kind of all over the place. And those particles have like cement. There's some kind of cementing material, right? And here's this St. Peter sandstone. It's 30 meters under my feet right now in Minneapolis. And you can see this cross section. This is 0.3 millimeters here. So you can clearly see grains, right? And you could talk about, those are grain contacts. There's arrows. You probably can't quite see them. There's an arrow here. Those are grain contacts. But then there's also other stuff. There's like here. This is sort of like, at a different length scale. At this length scale, you could say, well, that's kind of like cement. It's a big blob of cement that's joining those two grains. This rock already has enough initial damage in it. You can see this guy's cracked. You can see this is probably an open fracture, right? So this is the reality for the example of a sandstone. And I'm going to argue that this is, if we want to have a model of this, we can have cemented grains. And not just cemented grains, because we don't want cemented grains that are hexagonally perfectly packed. We want heterogeneous. So we want a collection of cemented grains that are arbitrarily arranged so that if you squeezed it, for example, in any direction, you'd get the same response. If you did a UCS test in any direction, you'd get the same response. So that would be an intact isotropic rock. So if we can somehow create a heterogeneous material of cemented grains, that's what I would say would be a reasonable model of intact rock. And that's a very complicated system, cemented grains, right? And so the macroscopic response, every single one of these things here we can think of this as like, these are all orthogonal to one another, right? An obvious one, degree of cementation. If we change the proportion of cement in there, we're going to radically affect the stiffness and the strength, right? And then there's additional things besides cementation, right? The grain properties, right? The size, the shape, the packing, all that stuff. There's also can be locked in stresses in these systems, right? They're squeezed, the sandstone gets formed because it gets laid down. Then there's tectonic compression. And then at some point, cementation occurs, right? That sandstone is going to have locked in stresses. That's part of the reason why you get core disking when you take out samples sometimes, because there's locked in stresses, right? As I said, these can be thought of as orthogonal things. Each one of these influences the macroscopic behavior. And all of these things evolve under load application, because usually when we're interested in modeling rock like this, we're interested in starting to approach its strength and seeing how it's beginning, how is it going to fail, right? And so we have this system that starts out as heterogeneous cemented grains, and then we start having damage in the cement, and then at a secondary level we can also have damage in the grains as well. Okay, let's talk a little bit about how intact rock behaves. So again, we're talking about brittle mechanical properties, right? Things that we see in the laboratory, that we see at stresses corresponding to near the surface of the earth. So we say, oh, we got this rock, and the question is, what are its mechanical properties? So we're going to say, oh, well, we're going to do these compression tests on it and measure some properties from those. We're going to do tension tests on it. We're going to measure some properties from those. And really, when you talk about failure, you can talk about two modes of failure, right? You can talk about let's start over here. An extension fracture, the simplest case. You just glue the ends of the specimen to steel plates and you pull it apart, and you tend to get a single localization that sometimes often will follow the path of the grain boundaries. Usually in direct tension tests on most rock, the grains do not split. The damage goes between the grains and it tries to form a path that's perpendicular to tension. Also, for the rock mechanics people here, they know about this. If you take a rock specimen and you squeeze it in a UCS test and there's no confinement, what you tend to get are these fractures that form parallel to the compression, and you get one or more of these, and we call this axial splitting. You basically squeeze it and it dilates and it causes tension. And so we get axial splitting. These I'm going to designate as extension fractures, meaning that the material on each side is moving away from each other, directly away from each other. So I'll call those extension fractures. But if you take a UCS specimen, but you now apply confinement to it and you do a test, once you reach the peak strength, what usually happens is you see a localization at some angle, and this is a shear fracture where you're getting relative shear motion on each side of the thing. Okay. The basic properties that you're going to get are really can be thought of as arising because of the microstructural arrangement. And again, if we were going to classify rock into just two categories, we could talk about these two different arrangements, right? This is compact rock. There's very little porosity. The only porosity in these systems would be initial small cracks on the grain boundaries usually. Here we have a sandstone. It's a whole different beast. And here you're seeing one with all sorts of pore space that's left over between these grains. And here's grain contacts with the arrows. This is 100 micron example here. Okay, so this would be a sandstone. There's much more porosity. And obviously there's ranges of sandstone from very, very well cemented sandstone to very poorly cemented sandstone. The damage that you get when you do compression is what you tend to see is you either see dilation or you can see compaction. And the reason you're seeing those things is because you're starting to get microstructural changes. Okay, so let's talk about if you just had a granular system versus if you had a more compact system. So this is just be a granular sand, right? And so if we apply deviatoric loading, right? So that means we're compressing with a value of stress and we're confining it with a different value. So those two different, the difference of that stress is the deviatoric. So if we have deviatoric loading, you tend to get dilatancy. You squeeze it and it bulks out like crazy. It increases in volume. And that's happening typically because the grains are slightly readjusting and repacking. And as you force them to repack, they end up dilating. So that's if you have deviatoric loading. If you have compact rock, you also see dilatancy, but now it's not because the grains are rearranging and repacking, it's because you get a microcracking. And you're getting dilatancy, you're squeezing it vertically, you're getting expansion here, and it's usually because most of the cracks again are oriented this way. So if I squeeze it and I get a crack going vertically, that causes a little bit of opening in the horizontal direction. And so in compact rock, you're getting this micro cracking, which is giving dilatancy. In porous rock, it's much more complicated. People talk about, let's talk about this one first, deviatoric loading. So again, you're getting dilatancy because of microcracking, or sometimes you're actually getting a compaction band happening where you're actually getting a localized, relatively thin layer of 4 or 5 grain thickness where you're getting grains crushing and compacting in a localized region. Okay, we talk about shear enhanced compaction. This depends upon the tightness of the initial sandstone microstructure. microstructures that are relatively porous will sometimes exhibit this compactancy behavior. Under hydrostatic loading, which we often do with porous rock, right? We just get compaction. It can't do anything. It can't dilate. It's being squeezed in all directions, right? And then we eventually reach a point of crushing of the grains. Okay. Now, let's see, what's my next picture there? Let's go back. Let's talk about this. People have, ever since the late 60s, people have been doing experiments on rock, and almost all experiments are typically done on cylindrical specimens. They're usually 2-to-1 high aspect ratios. And what they do is they do these experiments, and they measure stress and different types of stress and strain. And then they look at different sorts of behaviors going on at different points in the process. So they're basically taking a rock and running it through a strain path and looking at the damage that's happening. You can then, during a UCS test, so what do you do during a UCS test? You're applying displacement, you're measuring sigma 1, which is the force on the platens. You have a confining fluid that's applying a sigma 3, and you're typically keeping that constant. If you keep it constant, we call it a triaxial test. And then you're typically measuring, somehow you're measuring axial strain, either by the displacement of the platen, or you can actually sometimes, especially for nice competent rocks, you can put strain gauges on there. So you can measure axial strain, you can measure lateral strain, right? And then what do you plot? Here's the first thing: stress versus axial strain. And this is your UCS. This is a UCS test. And this is actually real data for granite called Lactobane granite. Lactobane granite is about 7-hour car drive north of where I'm sitting right now. If I go 5 hours north, I hit the Canadian border, and if I have my visa, my passport with me, they let me in. And then I drive another 2 or 3 hours, and I get to a small town by a lake, and that town is called Lactobane. There's a quarry there where they take Lactobane granite, and you might say, why do we care? Because about an hour away from that quarry is where the Canadian government had a big, huge underground research laboratory. That laboratory was running from probably late 1980s until the early 2000s. And that was where they were doing in situ testing that was in support of long-term storage of radioactive waste. And so the rock in that underground laboratory was Lactobane granite. And so there's been an unprecedented amount of laboratory testing data for Lactobane granite. As far as I'm aware, it's probably the best data set for any rock that we have. And so we're going to use that as an example of these different stages. We're going to talk about the stages that occur during a UCS test, and certain stresses during these stages are going to be, we're going to talk about as characteristic stresses of a material. This analysis of the behavior of a compression test on rock applies to all rocks, and you can map these things for all rocks, but this is going to be uniaxial compression of a granite. This is actually data for a granite. The other thing to be said, so these curves were created and talked about by a paper by Martin and Chandler. Both of these guys were very much involved in the radioactive research back in the time of the Canadian URL. They defined these 4 stages, which I'll talk about. These stages, this was not defined by them. This was defined by a guy named Benioski in 1968, who was the first one to do careful testing and start to talk about the different types of microstructural damage that's occurring during a test. So with that as a precursor, let's dive into this. What are the plots we're showing? First of all, axial stress, axial strain, just measured with the stress on the surface. So with that's axial stress, axial strain, this is lateral strain. This is bulking. Okay, how much is the radius changing over the initial radius? Okay, And then this is volumetric strain. And this is such that, again, this is versus axial strain, same thing, versus axial strain. This is volumetric strain such that this is contraction. It's getting smaller in volume. And this is dilation going negative. Okay, so let's talk about this. The standard stress strain curve. What typically happens is you get a little bit of an increase of stiffness. And then once you reach a certain point, the stiffness stays the same. And this increase of stiffness here is attributed to the fact that most rocks have initial damage in them. The initial granite itself has all these little uh, cracks at the grain boundaries usually. And what you're doing when you first start to compress it is you're closing those cracks. And so if you start to close cracks, you're stiffening the system. Think about it in the world of PFC. You have a crack, you have an opening between two grains. You start the grains come in contact. There's a spring that gets put there, right? So more springs, more stiffness. That's what's happening in rock. So we call this the crack closure region. And this is the characteristic stress, the crack closure stress. Then we have a portion where the stress strain response is linear. And this is where we are supposed to measure the elastic constants, the E and the nu. Okay. So we call this the elastic region. Okay. Let's talk about, notice here, this is lateral strain. This is lateral strain means it's bulking out. And so basically this part is pretty much linear. You're squeezing it and it's elastically, you're closing the cracks and now it's elastic. And so it's bulking out. And meanwhile, it's contracting. It's getting less and less in volume. Okay. So then we reach this point where we call it crack initiation. And what we see is we see tensile cracks that form that are parallel to sigma 1. And these tensile cracks tend to be distributed heterogeneously throughout the specimen. They're not localizing, they're just cracking and then cracking somewhere else and cracking somewhere else. Okay. This can be measured. I'm not going to go into this by making this plot, which is basically looking at the volumetric strain that you're measuring versus an assumed elastic volumetric strain. And what this means is that the volumetric strain is no longer increasing as much, that the specimen is no longer contracting as much as it would be if it was still elastic. And so we can measure this. We call this crack initiation stress. For lactobonate granite, it's about 40% of the peak stress. You also start seeing this, the lateral strain is no longer linear and it starts going faster. And that is also that's an indicator that suddenly the bulking, you're getting these cracks and it's bulking more than it would if there weren't cracks. So they call that crack initiation. And they also talk about stable crack growth, meaning I could stop the test and it just sits there. Okay. There's no sort of interaction going on between these microcracks. Then we get to a point here that corresponds with what we call this the crack damage stress. This is the volumetric strain that we're measuring. So notice the strain, it's getting smaller in volume, it's compressing. Oh, holy smokes. Suddenly, there's so much damage happening that this thing is starting to increase in volume. It's starting to go down. The volume is, so it's bulking like crazy. We call this crack damage stress. We're getting significant. Notice the lateral strain is huge. It just starts taking off. Okay. We call this the crack damage stress. Here's some things you might not know. When they refer to this region as unstable cracking is beginning. Basically, the system's getting really close to failure. If you keep on loading slowly, like in a UCS test on a standard specimen that's 50 millimeters high, so if you load at that rate, the stress will keep going up and eventually you'll reach a peak and then there'll typically be brittle failure, axial splitting, and this stress will then just drop. Okay. And this is what we call the UCS. Now, what you may not know is for lactobonate granite in particular, If you take this specimen and you load it up, let's say to 90% of peak, you just keep running your test, your normal loading test, and you get to 90% of peak, and then you just stop the test and you turn on a servo mechanism to maintain that value of load. Just maintain it. And then you go and you walk out of the door and you go home and have dinner and you come back later in the evening and you will find that the specimen will have failed. And it's like, what the hell is going on there? Because I loaded it, it should have been stable. I just kept the load the same and I waited a while and it failed. And what you will find is that the closer you are to peak, the sooner it will fail. If you load this thing just past crack damage, it might take a month till it fails. Okay. And then it sort of starts to go off an exponential thing. If you load it right around crack damage, we don't know. Tests have only been done out to about 6 months, as far as I'm aware of. Okay. The idea here, though, is that once you reach this state, you've got so much damage going on that you're activating a different damage mechanism that's time dependent. Under constant load, it's creeping. Why? The reason is there is a mechanism that's called stress corrosion that occurs in silicate rocks. And what is stress corrosion? Stress corrosion is, I can explain it first of all in for a glass. Okay, if you have a glass and if you machine a crack in it, so now there's a well-defined crack tip, and if you pull it in tension, okay, so if you put a crack in it and you slowly pull it in mode 1, you'll reach a point where it'll rupture. And they talk about that is the K1 that corresponds to the toughness, K1C, right? But if you load it up below the K1C, and if you keep the load constant, that crack will slowly grow. And in the case of glass, a silicate glass, what's happening is that at the molecular level, there is a chemical reaction that can occur with the silicon dioxide and the water that will effectively reduce the strength of the surface. And that chemical reaction happens exceedingly slow if there's no strain on the surface. But if you have large stretching of the surface, you start to make that reaction happen faster. And so at a crack tip, you have extremely high strain at the molecular level right at the tip of the crack. And so what happens is this stress corrosion starts corroding the tip and making it grow longer. Okay. And this is all totally understood, totally well described in the ceramics literature and in the original work in the 50s that was on glass, because you can show there has to be water. If you do it in alcohol and you pull the thing, it doesn't do anything no matter how long you hold it. So there's a chemical reaction called stress corrosion, which occurs at the molecular level at the sites of very high strain. And so it occurs at the crack tips. So remember our system here. At this point, we have quite a large amount of micro damage in here. And some of those sites are getting tension high enough that it's activating stress corrosion. And as that stress corrosion proceeds, eventually as it proceeds, there's the cracks are getting longer. So there's more and more damage. Eventually you reach enough damage and it fails. And the idea here, and also as you load up closer to peak, there's much more damage to begin with. So it doesn't take as long for it to eventually fail. And there seems to be a threshold below which you don't get this damage. So we can talk about this as being the long-term strength of the rock. So this is stress corrosion. This really happens. This happens in sandstones as well. I've done a lot of research in this area, and so I know all about this stuff. I even wrote a journal paper that talks about how I was able to make a bonded particle model incorporate stress corrosion mechanism. And yeah, most people in rock mechanics don't know about this, but it really happens. And when we design excavations and openings and stuff, we always design them so the stresses are below. They're never near the near the UCS peak. So this is a time effect that starts happening. So these are the 4 stages that people talk about that occur when you do a compression test on rock. The bonded particle systems, many of them, so when people build these, I'll call these microstructural models, because they're not just bonded particle models. People can build other systems where they take like tetrahedra. They take a finite element mesh of tetrahedra and they put bonding in and little interfaces in between the elements. And then they go and they load that and they see all the same sort of behaviors as you do from a bonded particle system. So any of these microstructural models, as long as they produce micro tension when you squeeze them, will exhibit these different behaviors. And so what people do to try to gain confidence and so-called validate these models is you say, okay, if I want to calibrate my model properly, I need to know this data for the rock, and then I need to basically do things to the microstructure so that I can match these different points. Okay. Many people who do this modeling do this for lactobonded granite because the data actually exists for all these different points. In all the bonded particle modeling work that I've been involved with up until a year and a half ago, we've been able to match the first 3 of these, but we have not been able to match this point at which we get volumetric strain reversal. In most bonded particle models, you don't get this. You don't get volumetric strain reversal until it all starts to fail. Okay. In this new work that I've recently been involved in, where we build microstructures that are Voronoi cells that perfectly fill space, and then we put in a simple bonding model at the faces here, the internal faces, we've been able to actually match all of these things. But the key thing we needed to do is we needed to have a criteria where these grains can actually break. And what we find happening at this point is when the grains break, they start causing huge amounts of bulking. And that's what's causing this drop then and this reversal in the volumetric strain curve. All right. So, and then everybody that does bonded particle modeling doesn't talk about time effects. They just keep loading and they get a UCS. Okay. And again, there's work I've done where I've added this stress corrosion mechanism, but I'm not aware that very many other people. They're just starting to be researched now, where people are starting to look at this time dependency on these systems. Okay, that's the high level picture. Now, if people say, why do we get such complicated compressive behavior? They say, well, there's these flaws in the rock material at the microscopic scale. And what you say is they're describing it as there is this proliferation of this damage and eventually it localizes. Okay. And so if you want to have some sort of a basis for doing theoretical developments of like what's happening and what needs to be going on in a rock, you need to have a structural description of the rock that can actually allow these things to happen. Okay, and that it can evolve because there starts to be more and more damage, that things can change as there's more and more damage. Okay, I would argue that the bonded particle methodology can really be thought of as a full-blown micromechanical theory of brittle failure. Okay, because what can we do? We can make all sorts of physical models that exhibit these behaviors, that exhibit all the behaviors I've been talking about for the brittle space of damage. And they allow you then to change microstructures and see what effect it has, right? So you can do experiments. So this is the key point about this. I would argue that these types of models can actually give you, they explain the brittle failure process. All right. Now, one more high level thing here. Let's talk about two different materials. One of them is the material we've been talking about, right? Where we have a cemented granular material, right? And so because of its cemented granular material, it will naturally produce these tensions. So it produces microtension and then it allows for bonds to break. That's the material we've been talking about. An alternative material would be a linear elastic body with a whole bunch of cracks. Okay. And what you have to have is if you have cracks in a system like this that are oriented relative to sigma 1, what happens naturally at the tip of this crack here is that you get tension in this direction, because basically you're pushing that surface that way and you're pushing that surface that way and you're pulling open the surface here. And if you have a concept of fracture toughness, then you can say I squeeze this and then notice I'm getting this extension of these cracks. Okay, so the fact that the cracks are oriented relative to sigma 1 gives you microtension in such of a system, and it gives you crack extension because you get these, they call these sliding cracks. Okay, so you could build such an idealization of a rock, and this idealization of rock will give you most of the properties of those four stages of a compression test, but you have to have a population of these things. Okay, so let's apply both models to trying to explain why axial splitting occurs. Okay, so it occurs because it starts off from these local tensile stresses that naturally occur at flaws and heterogeneities in the rock. This is true. This is really in rock. I spent the whole summer last year reviewing as much literature as I could find of microscopic and other means of determining damage in rock specimens as they get loaded. And there's basically what happens is you generate all these tensile stresses, and these tensile stresses start to cause damage. And these tensile stresses exist because you have flaws and heterogeneities. So in both of these idealizations, you get axial splits nucleating, right? They start happening as broken bonds in a BPM and as these wing cracks in an LEFM material. And then they start growing into an orientation parallel to the direction of compression. In the LEFM material, you get these lengthening wing cracks, and in the BPM, you get a coalescence of these broken bonds, right? Now, the bonded particle material, it has some things that the other one doesn't. So not only do we have microcrack nucleation, which you have in the other model by those wing cracks starting, you also start having growth and eventual interaction. This wing crack model only goes for a little bit, and then once it can't handle these guys interacting with each other. Okay, the bonded particle system is much more what's the right word? Far richer than the LEFM system. In the LEFM system, you have these two rocks with these two radically different microstructures, but if you want to model them, you have to come up with an equivalent set of cracks and their orientations in a linear elastic body. Okay, whereas in a bonded particle system, you can directly mimic these microstructures. Okay, in fact, one can take bonded particle systems and look at the fractures that form, and you can interpret them in terms of linear elastic fracture mechanics. And so linear elastic fracture mechanics behavior is itself an emergent property of a bonded system. Okay, you can take a bonded system and you can machine in a crack and you can do a mode 1 test and you can measure its fracture toughness, right? That just would naturally happen in a bonded system. Okay, so I'm trying to argue here, this is the different way of thinking about this thing, right? This is a very powerful model of rock because you have this clear connection between the microstructure because you're mimicking aspects of the microstructure.